Right, perfect. Thanks, Miho. So yeah, this is presentation on the Council Danjo Fitzgerald Boardwalk in Mallow. And I'm just going to give an overview of the project, and Kieran and Peter will deal with the design and structural elements and building of the structure. So I suppose first thing really is, what's this boardwalk in Mallow? So we constructed a boardwalk to the side of the existing Mallow Bridge to improve pedestrian safety and usage. To do this, we removed the existing footpath on the bridge, and the additional space that allowed in between the parapets, we were able to provide two turning lanes, which gave a much greater flow of traffic and safety to traffic on the bridge. So there was bonuses for pedestrian safety and active travel, and for traffic flow in Mallow Town as well. So just move on to the next slide. Just to show you, hopefully the pointer will work now. Yeah. So that there you can see on the pointer, that's Mallow Bridge. And as you can see, it's a real focal point and connectivity point for the town. So it connects obviously north to south, but it connects residential areas with the commercial centre and schools, and it's a real important place for Mallow Town. So just on the next slide there, you can see before the project commenced, we had public consultation, and it was proved very useful. And story which I'll tell later on the presentation, Mallow Field Club, which is a historical society, came to us at this meeting and asked us if we could do something during the project. But as I say, I'll explain that shortly. So the advanced communication to all stakeholders and to the public and residents alike was a critical and very important part of the project. So again, just in that regard, as you can see, we had a website, a web page on Cork County Council's website about it. And our chairman, Miho, he created a fantastic 3D concept video of it before construction. And that was very useful to explain the project to members of the public and everybody that needed to see it. It was a fantastic tool for that. So we obviously had some press, some press articles about it, and we prepared a newsletter as well in Cork County Council, which we found very informative for the elected members and members of the public to let them know what was happening and what stages the project were at. So then just a little bit about Mallow Bridge. This is a photograph of the bridge before any boardwalk was built. And just to give you a small bit of the history of the bridge. There has been a bridge in this location in Mallow since 1615. And since 1615 to 1712, there were three timber bridges. There were three timber bridges here, but each one of them was swept away subsequently by flooding. So it is thought then that in 1712, the first stone bridge was constructed. The original bridge comprised of 15 equal span arches. It is thought that 11 of these arches were severely damaged during the Great Flood of 1853, and for this reason were demolished and replaced by 4 cut-washed or limestone arches. So I'll just explain that to you there in the picture. So as you can see, the original bridge, this is the smaller arches bridge here on the left-hand side. So originally there was 11 of those arches spanning all the way across the bridge. But then in the Great Flood of 1853, they were swept away. So then these 4 limestone arches were constructed. So this is one of the challenges which the lads will be going through later on. We were dealing with 2 different structures. So we're dealing with the original bridge and the newer bridge. And that created many difficulties, I suppose, with the different types of construction and material used, and in their geometry. There are different geometry, both horizontally and vertically and curvature-wise. So that was all challenges to fabrication of the structure and the construction of it. So I'll just move on to the slide here. One of the main issues on the old bridge, as you can see in this photograph, is there was a very substandard footpath width-wise. For example, if you had a buggy or a wheelchair user, as you can imagine, walking here past the utility pole, and likewise someone coming against it, you often had a dangerous situation where someone had to step onto the footpath, onto live traffic here, which was quite dangerous. So along with the construction of the boardwalk, we also upgraded the adjoining junctions, and we made them much safer for pedestrians and vehicles alike. As you can see here on this photograph, you can see, oh, sorry. Go back to now. So yeah, as you can see in this photograph, you can see the HGV, the truck mounting the footpath there. And you can see pedestrians, even a pram, a lady with a pram here, standing back and letting the truck continue its journey, which is obviously dangerous and not an ideal situation. You can see here again the tightness of the turning junction. So then this is just a map of before and after. So as you can see beforehand, that there is the narrow footpath. This will become clearer in subsequent photos, but basically you really only had one lane in each direction with turning arrows for turning at the junction. They were non-standard. But when we were able to remove the footpath and suspend it by a boardwalk on the side bridge, we had much more space available to us between parapets, so as we were able to install dedicated parking lanes, or sorry, dedicated turning lanes. So we get a much better through flow of traffic across the bridge because traffic wasn't being blocked and held up. So again, that will become clear now in subsequent photos. So here you can see the photograph. As you can see, that was the old setup, no dedicated turning lane. What used to actually happen is if two cars came here to turn right, they would block up all the traffic inside here because no one could pass inside to go straight ahead and go left. So that used to actually block up all the traffic in along there towards Clockhouse and Mallow, and it would affect traffic throughout the town, all because of this point here and the inability of traffic to pass by. So this is just a picture for the construction. Peter and Kieran are going to talk much more about the construction. I suppose at this stage, I must praise the contractor, Cumner, and also the their subcontractor, that did the metal fabrication, Mac of Nina. They did a fantastic job, very high quality work. As Peter and Kieran will be going through the many difficulties and constraints, and the difficult geometry was there, and it's a fantastic job done by all. I suppose also on this slide, just to say, during the construction, it was constructed off-site and then brought to site to fit the bridge. So there was very detailed surveying required and 3D modeling because as I said, it had to be built in the factory in Nina and then transported to site and fixed the bridge. And just to mention my colleague Flora Henley, who did excellent surveying and 3D modeling work on the project as well. So again, that's just that situation again at the junction. Just to show there, you can see the footpath continually being broken up by vehicles mounting it, and you can see pedestrians were getting crushed here, or little or no space for them to safely pass with the barriers. So the next slide now should be after. So as you can see, we hugely improved the junction from an aesthetic viewpoint and safety viewpoint. And just to mention there, our consultants, Brady, Shipman, Martin, who helped us with the design of this amenity area and the paving, etc. And as you can see from the photographs, it looks very well. So basically, as you can remember before, pedestrians were right up against the turning trucks and adjacent to vehicle movements. But now the footpath, as you can see, continues on side here. And pedestrians walk down here. They're segregated from traffic by the vegetation here, and they can have a much safer and much more pleasant journey. And again, as you can see in this photograph, it's a nice amenity area in a focal part of Mallow town. So then this is just an overview. You can see the boardwalk along here. Again, that's just an overview of the junction safety improvements that we did. And you can see here the dedicated traffic lanes where anyone now that wants to turn can go into their lane and stack up behind if necessary, and you can still allow free flow of traffic. So again, that's just a picture of the boardwalk structure itself. And again, that's the laneways on the roadway. So this was probably the greatest pinch point for traffic disturbance on the old bridge or delays. As you can see now where these cars are, if anyone wants to turn right there, they can go into their dedicated lane and wait until they get the appropriate signal, and all the traffic then can continue on, turn left to go straight, rather than, as you can remember in the earlier slides, where there was no dedicated turning lane and any couple of vehicles wanting to turn here was causing back up the traffic. So just to mention there, another consultant we had on the traffic design and because obviously all the junctions and the adjoining traffic signals had to be upgraded, and Arabs were our consultants in that regard. So, as I said there at the start, during our public consultation meeting, Mallow Field Club, which is Mallow Historical Society, came to us with a story about this plaque. So, as you can see on the left-hand side is a plaque. This actually was a plaque which was produced in 1586. And if you can remember back to the earlier photos, it was for the 4 limestone arches that were built at that time. So it transpired that this plaque was discovered in 1980s when there was a commercial building being developed in Mallow. They were doing the groundworks, and lo and behold, while doing their digging, they found this plaque. So it transpired that on the site they were working on 200 years ago, there were Cork County Council sheds there and storage sheds. And obviously this plaque was left up there and never got to go on the bridge. So we were asked to know that when we were doing our project that it would be nice if we could bring it back to the bridge. So we totally agreed, and thanks to everyone that gave us the permission to relocate the stone. So as you can see here on the side, we got it all cleaned up and restored. And just to explain, the word on it, Grand Jury Pressement, that's actually apparently what local authorities were called hundreds of years ago. This here is what it was constructed for in 1856. That's the 4 new limestone arches, and Cowley and Co were the builders. So it was nice to bring back a bit of heritage back in the project when we got the opportunity. I suppose another opportunity that we were able to take was we relocated this Celtic Cross monument for the War of Independence. So as you can see here on the left-hand side, it was located up on the bridge, on the old bridge, and it's right out here on the traffic lane. So nobody could really go and visit the monument or read the inscribing or anything like that. It was actually dangerous to go and stand there. So I'm going to go back a few slides now and just show you where it was in an overview. Yeah, so actually that's where it was located there, where my pointer is. And as you can see, anyone that was going out there was putting their own life at risk because they were right out in the traffic lane. So we were able to locate it here. This is it here now. We were able to locate it in this large plaza area that we were able to develop when we were building the boardwalk, and it's also new entrance to the town park. And so going back to the other side, it's obviously a much more safer location now. And every Easter they have a commemoration there, and they had so much space there. Last Easter they even had a pipe band there. So obviously anything like that couldn't happen in its previous location. So that was another nice bonus that we were able to incorporate with the project. So that's just a picture of it at night time. Peter will probably talk a bit more about that, but as you can see, it was very well lit up with downlighters from handrails and some uplighters on the piers, and it looks very well. So that's me for now. I'm going to invite Kieran to talk and give his presentation.
I suppose specifically, I want to talk to you this evening about the structural design aspects of what ultimately was quite a tricky bridge to design, even trickier bridge to build. But from a conventional point of view, things that kind of made it tricky were more to do with the constraints of the actual job, more so than the actual design parameters. In the end, it's a reasonably straightforward bridge when we finally got down to our chosen design solution. But from a detailing and construction point of view, it did have a few different intricacies that I kind of just want to talk about this evening. So as Kevin mentioned, it's a fairly decent focal point in the town of Mallow. Realistically, there's 3 bridges in the area. It's the old railway bridge. There's the N22 or the N20 bridge, which is basically almost like a kind of a bypass. And then there's the main bridge in the town itself for what's reasonably big population. The next bridge downstream to the east is about 9 kilometers away in Killavullen, so it is quite a focal point, as Ted mentioned. And as such, being a focal point, it had fairly significant local interest and concern, which much to the contractor's pleasure, a lot of Mallow residents, they keep an eye on the job with eager eyes as they're passing on their daily commute. So this job has been around for a while. I think Malachy, we did the preliminary report back in 2007 or 2008, and it kind of went through a number of different phases, and we ultimately won the tender to design it back in 2018. And specifically, the design brief is simple enough. It was provide a pedestrian walkway outside the west spandrel, allowing the removal of the existing footpath inside the parapets. And within that, then the key objectives of the project, I suppose, were to allow for that extra turning lane and to improve the pedestrian safety. What we were tasked to do, I suppose, is come up with what was ultimately a value engineered lightweight solution in order to construct this boardwalk, because dealing with a historic structure, an existing bridge, we kind of want to, I suppose, the smallest intervention possible. And then within that, then, you know, we also had to keep the bridge traffic flowing at the time of construction, so we needed to ensure that we were sort of minimizing the amount of intervention, and also in keeping within heritage and preservation principles. One of the key aspects is that ultimately that this boardwalk can be taken away later if it needs to be, at the end of its design life or at the end of its useful life. The bridge is going to be there for a long time. It being a limestone bridge, the steel in it, however, is probably not going to last as long as that. So ultimately, within these kind of projects, the best practice is to design it in such a way that it can be removed at a later stage, which I think is what we kind of achieved. So within the design of it, then ultimately, this is kind of a simple outline of what we were ultimately tasked to do. On the western spandrel, the lower side here, on the upstream side, we were to construct this, to design and then ultimately have the construction of this particular boardwalk. Within the design constraints, the first biggest one, I suppose, is that it is a national monument. The bridge itself is a gorgeous old bridge, and it does limit the amount of things that you can do with it. If this was a regular old bridge out in the middle of nowhere, there's a lot of different options you can have to widen it to get that additional traffic lane, or multiple traffic lanes, or multiple footpaths if you want. But when you are dealing with a national monument, there is a limit to the amount of things you can do, and you have to work closely with your conservation architect, with the National Monument Service, in order to come up with what is ultimately an acceptable solution. If anybody knows the areas from the area, you'll know that there is a significant history of flooding around the bridge. That whole area to the top there is a town park, which is usually a green area, but in high flooding scenarios, the whole thing can be pretty much submerged, and it does put an awful lot of flow and a lot of additional pressure on the bridge itself. Down the lower corner here, you're going to see parts of the flood defense schemes that have been constructed, which we also have to interface with within our design. In addition to it being a monument and all the flooding that we have to kind of look to trying to work around, and there is a significant presence of services within the carriageway. Now, I'm not going to speak a whole lot about the services. I think Peter will touch on some of them in his presentation. But for what is ultimately not a huge amount of space, there was, when we were looking at the bridge, we did see cut into some of these limestone pieces, service ducts actually shaved into it. So the actual service ducts themselves actually almost became part of the structure almost, and it definitely did provide a fairly significant constraint for us when we were designing, such that we had to try and upgrade these services, but we also had to make sure that we couldn't disrupt them too much. And then, as I mentioned, we had to ensure that the bridge was open throughout the working period, throughout the contract. Minor closures allowed for such as the installation or the erection of the steelwork itself, but for the most part, pedestrian and vehicle traffic had to be maintained throughout the contract. And as Ped mentioned, it is ultimately two different bridges, and you can kind of see that here, as we've got the old and more rural stone, smaller arch bridge, and then the cut limestone, larger arch bridge. And the consequence of that as well is that those two bridges are actually at a slight angle to each other. There's not a straight line on the bridges, but a 14-degree kink in it, and even within that 14-degree kink, any straight line that you think exists on the bridge doesn't really exist on the bridge at all. And you can even see the extent of the flooding there if you look at the tops of the arch here compared to the existing water level. When you do look at the flooding from the previous slide, you can see that the water is pretty much up to crown level there at the arch. So again, you can't really understate how much flooding is an issue for this particular bridge. So within what we had to design is we were ultimately looking at about 110 meters of cantilever walkway, which, when we were comparing it against different solutions around the country, is probably on the longer side, maybe the longest side for this type of structure, for this type of widening. And it did, in addition to the 110 meters, we did have about 25 meters of a kind of an approach retaining wall abutment on the northern side, which we managed to kind of clad and interface with the design from Brady Ship and Martin and integrate it into the kind of that plaza area, that junction area that had been redeveloped. A big issue for us on the southern side then was integrating with the existing flood defense scheme. I said there was a fairly significant flood defense contract undertaken here in the past, and so one of the big things for us is that we didn't make the situation any worse. We had to interface with it as much as possible in order to preserve those flood defense schemes and ultimately integrate it into our design. And then again, due to the fact that this is an old structure, there is very little agreement in levels at any point within the existing bridge itself. Any of our landing points, any point on the bridge, generally speaking, in any direction, the levels aren't going to match up, which isn't exactly something that you ideally would be designing for, but it is one of the hazards, I suppose, that you have when you're dealing with an existing structure. So within the options for design, as I said, this has been kind of kicking around for a while. This was, I suppose, part of the original report, looking at how we're going to widen the bridge or how we're going to provide that cantilever walkway. This is, I suppose, one of the first options proposed, which is a kind of a triangulated type of truss structure, and essentially kind of a lightweight enough solution, supported vertically by a kind of a plinth or a reinforced concrete plinth projecting out from the underside of the bridge to above the cutwater, and then tied back with tension anchors to the spandrel of the far side of the bridge, which was, in addition to kind of giving that tension resistance, did provide a little lateral stability. Ultimately, when we're looking at this, it did kind of, I suppose, the services intervention weren't huge. There wasn't a huge amount of diversion, but the constructability of that plinth at the location of the cutwater and the potential impact on it being a national monument, we kind of wasn't one of our preferred solutions. One of the second options we kind of anticipated was this pile cantilever solution, which ultimately is a simple enough structure in the end, where we basically just have a cantilever beam and a set of piles on the inside of the bridge, essentially a tension and compression pile to kind of give us that moment resistance. The actual deck structure itself is kind of simple enough longitudinal beams and transverse beams. And while it kind of, looking at it from an elevation point of view, it's a reasonably visually unobtrusive structure, it is physically and structurally quite intrusive into the existing natural monument, which is kind of, I suppose, one of the reasons why we ultimately discarded it from the selection process. It was just felt when we were discussing it with our conservation architect, Garrett O'Callaghan from JCA, that it was potentially maybe too difficult to structure to kind of blend into the historic monument, and ultimately reasonably isn't that reversible, which kind of violates the principles that we had from the conservation and the heritage point of view. This has been done in recent times. This is a new bridge up in Navan, and it was successfully implemented here, and showing it can be done, but within our specific context here, it just kind of wasn't seen as being the appropriate solution. A version of it then that kind of minimized the amount of piling that we'd have to do within the carriageway is if we went for this kind of mass concrete counterweight option. Again, the structure pretty much would look the exact same from an external point of view, but rather than having this kind of tension compression pile solution, we'd essentially just replace it with a kind of a mass concrete counterweight. The big drawback of this particular option was that it was going to necessitate fairly significant diversion of services. So some of these services are fairly integral to the structure. So ultimately, this wasn't seen as being a kind of a viable solution. In addition to that, it puts an awful lot of additional self-weight onto the arch barrel themselves, as opposed to concentrating all the forces into the cutwaters, which we were ideally trying to do. This was kind of spreading out a bit more into the arch barrels themselves, and ultimately kind of we weren't wild about it as a design solution. This option is, I suppose, more standard for what you're seeing today within regards to widenings of, or these kind of cantilever steel walkways. And essentially, it's just a simple enough grillage system with hollow members with inclined kind of struts, vertical struts that take ultimately all the vertical and compression load back straight into the cutwaters of the bridge, and again tied back to the bridge itself, either through a horizontal tension anchor to the far side of the bridge, or a kind of inclined tension anchor back into the cutwater, where we have an awful lot of additional support. Again, quite a lightweight solution, reasonably popular. It has been used in a number of schemes throughout the country in recent years. This is the Macroom Bridge. The same kind of process is used. This is the M21 Tullow Bridge in Carlow. Again, you can see these kind of inclined struts coming out from the cutwaters. And here is the Carrick-on-Shannon Bridge. Again, you can see the struts actually projecting into the cutwaters here, whereas I think in the other two examples, actually had the removal of the cutwaters and then rebuilt them entirely, or at least built the capping zones entirely. And it's the Anna Livia Bridge in Dublin, which is a slightly more lightweight version of the solution, but again, ultimately dealing with a kind of an inclined prop, putting all that compression and vertical force back into the cutwaters themselves, with the tension anchors in the back, kind of keeping that lateral. Two other options in that we were asked to, I suppose, consider within the regards and flooding was that if, while all those options were perfectly viable, we were looking and we were asked about a structure with a kind of a flatter soffit. And we did look at, I suppose, two options in order to try and achieve that, just to kind of that cleaner appearance. This first option here is a kind of a box structure with this flat soffit and a kind of almost like a curve or a kind of a tulip type support coming out from the cutwater. Ultimately, all the compression for the vertical force is essentially being resolved kind of down at the top of the cutwater, and then the actual lateral forces based on these kind of series of ties bring it back into the standard wall itself. Very visually obtrusive appearance, especially at the location of the cutwaters. Quite a modern intervention. Wouldn't look terrible, but ultimately we found it very hard to come up with a construction methodology to actually safely build it, and therefore it kind of wasn't something that we thought was terribly viable without getting too intrusive into the actual structure itself. So we did kind of look at this and kind of ultimately decide it wasn't an option that we could really safely construct. And then this is a concept then that I borrowed from Laurent, a Belgian engineer who kind of proposed this type of concept for a masonry viaduct, but ultimately involved a kind of a triangular box section, tension anchors back to the far side, and then a kind of a compression pile here working in kind of shaft resistance, or alternatively kind of a bearing at the far end. But ultimately all the vertical force kind of being resolved into a small area here on the existing spandrel wall. While visually this would have been a very appealing type of structure, we ultimately just couldn't reconcile a reliable load pack for it, which ultimately does violate, I suppose, our principal kind of structural philosophy in trying to ensure that we do have this reliable load pad available to us. So ultimately, while it's actually probably a design worth exploring in future, but ultimately wasn't something that we found was particularly feasible within the context of this particular project. So we kind of started then converging, I suppose, more towards that inclined prop solution. But ultimately, if you look back at the previous slides, all of these structures kind of had reasonably shorter spans relative to the, we were dealing with 18, 19 meters in our major spans. In this bridge, these are going to more closer to 10, 12 meters. And what we were finding was that a pure inclined prop, it was kind of very high members, very large spans for the kind of what we're trying to achieve with a lightweight type of structure. So ultimately we did have to start considering different variations or different options on what was ultimately what we knew was a kind of a proven design. So we kind of came across this existing bridge in Italy, this Borgo Toskano bridge. And it had a historic structure that had a reasonably modern intervention by Enzo Severo a number of years back, were essentially mimicking the profile of the existing structure itself, and ultimately provided these kind of arched, inclined struts in order to kind of match that profile, which is a design concept that we ultimately unashamedly borrowed for this particular bridge. And we ultimately replaced the idea of our inclined struts, or vertically inclined struts, with this inclined arch. One of the big, I suppose, differences between what was done on those previous bridges against this is that in consultation with our heritage architect, we were kind of instructed and told that any sort of interface within these kind of cap limestone, the cutwater caps, was going to be unacceptable to the National Monument Service. So what we did have to do is come up with a slightly different variation on the scheme, whereby essentially we ended up raising the level of the base of these inclined or these arched props themselves, and then having this kind of compression mini pile system in behind. Now, ultimately, what that did for us is it gave us a bit of a detailing headache, in the sense that we couldn't bury the connection or the base within the existing structure and cover it back over with a capstone. We ultimately had to leave the connection exposed, and that did create kind of detailing difficulties for us in trying to come up with, I suppose, a visually acceptable solution for what was going to be quite a very apparent part of the structure. And we ultimately did kind of come up with this kind of fin plate and kind of cone anchor solution, which you're going to see within a 3D render in the next slide, but also you'll see a lot in some Peter's slides. And again, if all the compression force here, the lever arm and the tension forces essentially were on these inclined tension anchors as well, all of the force then being resolved back into the cutwater itself, which we had undertaken an enabling works contract back in the year before the construction that started, just in order to strengthen those cutwaters and give us that kind of additional support available. This is ultimately then the early kind of render of what the scheme looked like. There's some kind of refinements made to it since, but this is ultimately the type of structure we went to in our public consultation. And you can see the arched inclined arch here, and you can kind of see we have this kind of fin plate and this kind of nice kind of pin connection here at the base, which is, as I said, a fairly visual component of the structure. And again, a couple of other 3D renders that we used within the scheme, and you can kind of see here again how the whole concept looks as you're approaching the bridge from the town park or from the south side of the bridge. Again, kind of mimicking the profile of the arch barrel, kind of a parabolic arch ultimately, and then at the far side, these kind of half arches. We ended up ultimately rationalizing this back to a half arch as well, to avoid us having to build up another cutwater here. So we had a half arch here, and then where we have our smaller spans for the older bridge, we do have this kind of double span here that kind of mimicked ultimately the same span length as the spans for the newer bridge, the 1800s bridge. So within the deck itself, I said it's a reasonably simple typology when we actually start trying to resolve some of the geometrical details, but the actual structure itself is reasonably straightforward. Quite simply, main longitudinal member is our circular hollow section that essentially forms into our circular hollow section that forms our arch, kind of giving us that connectivity between the main longitudinal member and the arch itself. And we've got tapered hollow sections, kind of giving a nice kind of appearance on the inner side of the bridge. And then kind of two reasonably small square hollow sections, 200 by 10 SHS sections on the outside, left-hand side supporting the parapet itself, and then the right-hand side just giving that additional bit of support for the decking that we were going to be using. One thing that we I suppose to keep in mind is we did have to interface with this corbel a little bit as part of the old fabric of the bridge, and that did drive some of our design decisions later as to how we were actually going to fit out the bridge. And ultimately came out within what the main driver, I suppose, of the structural design was the buckling capacity of the main arch member itself. Essentially it's a pin arch with a decent enough free length, and ultimately the size of the section we use was kind of governed by that. And then in order to get that continuity to the main longitudinal member, we ended up repeating the size of the member. Ultimately, probably having quite a stronger structure than ultimately needed, but it does provide a fairly rigid structure, and we will see later that it does have fairly good dynamic properties as a consequence. And it works out at about 48.5 tons of structural steel used ultimately across the 110 meters, which ultimately from a self-weight point of view kind of has itself around 1.5 kilonewton per meter square, which isn't bad when it comes to a lightweight footbridge. One of the big components of the job after the design of the structural steel itself was the design of these anchors. And I said within a reasonably confined space within each individual cutwater supports ultimately the compression and tension properties of the bridge in order to give it stability. What we have down here are compression piles ultimately, which were drilled piles about 4.5 meters long at a minimum, and then grouted up to their annulus, and that was kind of giving that kind of shaft and bearing resistance into the cutwater itself. And a really tricky part of this was that we had to detail these to be diverging in order so we weren't, I suppose, compromising the integrity of any one of the piles. And while that's fine from a pure structural design point of view, it did create significant detailing and installation headaches in the sense that we do have these kind of what are diverging angles here are converging angles as we get towards the top of the anchors, and that did provide a bit of a headache, and it did provide a lot of prototyping of the base members themselves, and a huge amount of work done by Cumner and Mack in order to try and, I suppose, realize this particular design aspect. And then in addition to the compression piles, we had these tension anchors, which are essentially ground anchors that we were using to support the structure. Again, we've got this converging angle here, but it's not as severe at the top of the structure. And then ultimately, these ground anchors have ultimately, from a, I suppose, pure soil mechanics point of view, they have a kind of a free length and then a grouted length. And ultimately, that free length is basically to keep the grout out of the, I suppose, the active wedge of the bridge itself in the span to roll, trying to resist that mobilization of soil in behind the bridge. We did have the luxury of actually testing a couple of these to failure, in the sense that we were dealing with, I suppose, if we go back, we have a look at the slide here, we can see, there's two cutwaters that are ultimately unused within the design, and we did have good opportunity to verify the design capacity of our anchors, which is, I suppose, when you're dealing with a structure, this is a bit of a luxury. Otherwise, we would have ultimately been resulted to, I suppose, acceptance tests, but we were able to complete a number of plug tests in order to verify the capacity. And then lastly, as I mentioned, we do have the size of the elements, or the main longitudinal and arch element, are reasonably big big, just really driven by the buckling capacity of the arch itself. The consequence of that is that ultimately we did end up with a lot more mass, I suppose, than we'd ideally have to deal with for a dynamic point of view. Whereas when we did our dynamic assessment, we found that the bridge is actually quite in good shape under our first mode shape. What you're kind of generally looking for, kind of anything above 5 hertz for a pedestrian bridge, which means you're kind of in a decent range. We're kind of at 6.49. And funnily enough, the first mode shape was this kind of rotational mode shape. And you can kind of see, if we go back to the cross section itself, if you kind of look at it, the bridge is kind of hinging on this kind of center hollow section, circle hollow section, and the arch itself. You would think that we've kind of got not a huge amount of torque and capacity, but because of the welded connection, because of the grillage type system, and because we do have that very, very stiff core, we do have an awful lot of rotational and torsional capacity within the section. So it wasn't really a surprise to us when the first dynamic mode was this kind of rotational mode about the x-axis. But again, at 6.49 hertz, we kind of were happy enough with that. We were kind of not in any sort of in trouble dynamically. And then I suppose one of the more kind of common ones for pedestrian bridges is the vertical mode shape. That kind of came as the 9th mode shape with a natural frequency of 9.79. So we were kind of fairly happy that from a vibration and from a frequency point of view, that the bridge was going to be quite serviceable. And then even within that, then we did our acceleration checks just to make sure that the lateral acceleration limits weren't being exceeded, and they were all well under the allowable limits as well. So within then a couple of final design considerations, when you're dealing with any sort of pedestrian bridge, because people have a chance to linger, because they have a chance to walk across it, they do have a chance to touch the handrail, they do have a chance to look at the surfacing, unlike a road bridge where you're over it straight away. Our parapet design and our surfacing design were fairly decent considerations for us. So I suppose initially for the deck itself, we had proposed the use of a kind of a plate element with a kind of an epoxy resin on it, which you will see in a lot of footbridges these days. It's a lovely looking surface generally. But when we were discussing construction methodology with Cumner, ultimately we again couldn't kind of come up with a good, safe way in which to do it, especially when we're dealing with our tension anchors at the bottom. So if we have to try, and if you can imagine the deck itself up here, when we're installing it, if we were to install it with a plate attached to it, it would have to be welded in Nina, ultimately up in Mac Engineering's facility, and ultimately that would have prevented access to those tension anchors and would have ultimately been quite a hairy enough construction situation, which obviously we weren't keen on, and Cumner weren't keen on either. So we ultimately, I suppose, went for this aluminium type decking. And one of the good pieces of it is that because it was post-fixed, because it was essentially brought onto site afterwards, it did allow us a degree of flexibility within how we interacted with the existing structure. Because these can all be post-fixed, it was easy for us to, I suppose, give a nice lateral clearance for the structural member to the bridge itself, and then cover that with the aluminium planking later and allow it to be cut to profile of the existing bridge, allowing it to kind of have this smooth interface. Had we ultimately found a safe way to have the plate, it actually probably would have been, while on the face with the surface would have been nice initially, it would have probably had a detrimental effect actually in the fabric of the existing bridge, because we have this lovely little corbel here that is exposed. But if we had to try to fabricate that steel plate in advance, we probably would have had to give too much allowance, in the same way we've given an awful lot of allowance here to the main structural member, and we would have left with a gap here really, which ultimately probably would have had to have been masked over, more than likely with some sort of flashing in the face of the corbel itself, which ultimately would have been detrimental to the existing bridge. So the aluminium decking, which allowed us to post-fix it, ultimately did become, I suppose, the best design solution for the job. And then for the parapet itself, because we're dealing with the historic monument, we did want to minimize the amount of intervention visually on the elevation of the bridge, and we had proposed a glazed parapet, but in our discussion with our POPW key stakeholder in the project, they weren't particularly keen on the idea of a solid parapet, which would ultimately, in the event of a flood, potentially cause a rise in flood levels upstream, which kind of is not something they were particularly keen on, especially after spending a huge amount of capital on the flood defense scheme itself. So we ultimately revised it to kind of a traditional upstand parapet with some kind of detailing kind of edges, kind of stainless steel handrails themselves, and a kind of a vertical bars that were ultimately the same color as the existing bridge. So when you are looking at the bridge in elevation, you're kind of seeing, realistically, you're seeing a dark gray bridge, which is kind of blending into the background of the fabric of the bridge itself. And you're kind of, the only thing that's really jumping out at you is the actual handrails themselves. And then as you're walking along the bridge itself, you've kind of got that color continuity between the parapet and the structure below. And then you've got a kind of a color continuity between the handrails and the aluminium planks themselves for the surfacing. So that was kind of ultimately a kind of a design solution that was driven by a lot of practicalities and a lot of constraints, but ultimately I think the correct one. And you can even see here in this photo, you could kind of see the corbel here of the existing bridge, which remains exposed. So for any pedestrians using the bridge, they can see this part of a historic monument. The last things here is just, this was the fabrication model, which was done by Mac Engineering and their sub-consultants, O'Loughlin Project Engineers in Limerick, and they did a great job for us in detailing up this. It's a very tricky bridge. There was no kind of two coordinates alike, X, Y, or Z. It became a very difficult exercise, and essentially they were able to come up with a very intricate model that did give us a lot of confidence in how everything was going to be built, and ultimately ultimately fit in at the bridge on the day of the erection, which is always something you're hoping for, especially dealing with an existing monument like this. So lastly, then, as part of the consultation, we did have a number of renders made up as part of just trying to show the public what the bridge would look like. That's kind of an elevation and a kind of almost like an aerial view of it. And then when you compare it to how the bridge is photoing at the moment, it kind of compares reasonably favorably as far as we're concerned. So we're kind of happy with that. So like in summary, it's quite a complex project from a pure detailing and constraints point of view. We did, exhaust an awful lot of options in trying to come up with the chosen design solution. You can really, I suppose, say that you wouldn't change much about any sort of project, but there's kind of very little I change about this purely because there's very little you could change about this project based on just purely the amount of constraints we did have to deal with as part of the design process. And ultimately we did get, as a consequence, I do think we got a kind of a nice sympathetic complementary solution of this tubular arch, mimicking the profile of the existing bridge and kind of giving that modern intervention, but also, I suppose, respecting the bridge as constructed. And then, I suppose, purely from a travel and sustainability point of view, there's an awful lot of benefits to this project in the sense that we were able to reuse an existing structure. It would have been easy for us to go off and build a separate bridge or God forbid, demolish the existing bridge or whatever and rebuild it. Within, I suppose, the principles of trying to achieve a net zero design, they're not too far away from reduce, reuse, recycle for the most part. And whether, when reducing is kind of building less, I suppose, which wasn't really an option here because we did have to do something to structure. The reuse of an existing asset really did cut the carbon footprint of the project compared to what it would be if it was a new bridge or a different type of intervention. And again, the sustainability aspects from a travel point of view as well, even though the bridge now has much more vehicular capacity, it also has a lot more pedestrian and cycling capacity, which we think are incredible benefits to it as well. So I hope I was able to convey that it was a kind of a complex enough design process, but it kind of pales in comparison really to the construction process. So Peter is going to talk you through that.
Okay, good evening, everybody. Yeah, like I think a few other people, this is bringing back memories, been back in what used to be the drawing office in UCC. I'm going to talk mainly about construction issues now. I will recap a little bit about design issues. I've just picked 6 things, so I won't go on for too long. The first one is the fact that we're working with a national monument. The second one was the OPW constraints. Third was dealing with services. Fourth was COVID, which kind of hit us halfway through the construction project. The fifth was the traffic management that was required to enable the contract to happen. And the sixth was flooding. Now, Kieran has already mentioned some of the issues around flooding, but so it's more the flooding during the construction phase is what I'll be talking about. As has already been mentioned, the original bridge was oops. It's sensitive. Was built in 1712, 15 span masonry art structure. There was a disastrous flood sometime, I'd say 1855, 56, and following, during which 11 of the spans collapsed, and they were replaced in 1857 by the 4 main river spans that we see today, which hopefully will appear, down on here. So you have your 4 main river spans here, and then the original 4 spans from the 15 meter, from the 15 span structure. The southern the one other complicating factor is that the southern span, which you can see here in the aerial, is curved. And as Kieran has already mentioned, there's a skew between the original northern 4 spans and the southern 4 spans. Of the fact that the existing so the result of this was essentially it's a completely non-uniform structure. So a lot of the elements that had to be prefabricated were bespoke, and obviously ministerial consent was required to carry out the works, and a prerequisite of that is that we would have minimum impact on the structure. So each of the 6 spans, so the structure we were putting in had 6 spans. Each of them was supported by 2 top and 2 bottom. And you can see here, this one of the spans been lifted in. There's one of the top connections, and there's one of the bottom. So this is pure tension that Kieran has mentioned previously, and there's the compression. So you have 4 points of fixity for each of the spans. Each of those fixings then in turn was supported by 4 anchors, and with the compression anchors, which were 40 mil diameter, and the tension, which were 25. Because the construction tolerances associated with the drilling, and just go on to you've seen this slide already, because the construction tolerances associated with the drilling, essentially Cumner had to get these 4 anchors popping out in more or less the same spot. Now, you were never going to achieve 100% accuracy in that. There's always going to be a bit of drift. And the result of that was that each of these plates was bespoke. So that's a top connection, and this one here is a bottom connection. So your tension connections go on to these double plates here, and then your bottom curved arch comes down onto this plate here. There's a top plate then put in afterwards once this is all installed to stiffen this up. So again, there was a lot of surveying needed on site, and again, just every time I move this, these were recessed that we saw cut into the national monument. Okay. The OPW constraints, all new bridges, all new bridge works require consent from the OPW under Section 50 of the 1945 Arterial Drainage Act. This is to ensure that any works are not going to cause a flooding problem or exacerbate or make worse an existing flooding problem. On a new bridge, generally the requirement is that you would have 300 mil freeboard from the underside of your structure to the flood level. And the flood level is typically defined as a 1% exceedance limit, which is roughly speaking a 1 in 100-year flood, with due allowance for global warming. And there's confidence factors come into that, which tend to be higher in an urban setting than in a rural setting. So, and this is an urban setting. Now, however, in the case of Mallow, there's no freeboard. In a serious flood, it goes full bore. It flows full bore, and over the original 4 spans, there's a metal railing, and the reason for that is that in a flood, the water actually crosses the road here, so it flows over the road here. In terms of flood defence, the crown of the arch, which is over here, is part of the flood defence. So the northern part of the bridge is allowed to flood. The southern part of the bridge isn't. The flood defences are the actual parapet wall of the bridge and the crown of the arch itself. And then the northern half is flooded, and the flood defences are actually north of Park Road. So in a flood, Park Road is, and that would happen on a regular basis, that Park Road has to be shut off due to flooding. Now, I suppose this caused us a couple of difficulties. A, we couldn't satisfy the normal requirements for an OPW bridge, and B, then how do we prove that it's not going to be any worse? So there was, as I mentioned, well-established flood risk at Mallow Bridge that the normal Section 50 requirements couldn't be achieved. The steel arches on the boardwalk, while they're higher than the masonry arches, so the theoretical hydraulic capacity is fine, there's no issues there. However, there was a residual risk that the OPW had a concern about, that debris would get caught on the structure. So we did look at the possibility of moving the boardwalk to the east side of the bridge, but from a pedestrian point of view, that was a non-runner because that's not on the desire line, and there would have been safety issues associated with it. Ultimately, Kieran did a certain amount of redesign to minimise the amount of steel work that an errant trunk of a tree could get caught on, and Cork County Council have an agreement in place with the OPW that in the event, during a flood event, that there's a watch arrangement, so that in the event that something does get caught there, that it would get removed within a certain time period. So that's how, and there was a lot of toing and froing with the OPW to, they have genuine concerns. Obviously, any work that you do on a bridge cannot make a flooding situation worse. But equally, well, this was a particular, normally if you were constructing a bridge on the upstream side of the masonry arch, they look for you for the profile to be exactly the same as the existing profile the OPW do, but obviously that would have been completely unacceptable to national monuments, and that would have been masking a national monument. So it was a compromise really from everybody's point of view. And the other slight, I mentioned the fact that water flows over the road here. The implication of that was that our finished levels could not change on that section of the road. So because if we raise the road level there, that's less hydraulic capacity in a flood event. So, and that had implications for the services. Okay, the next point I'm going to talk about is just dealing with services. The existing footpath had a 225 diameter water main and a number of air and ESB ducts under it. The footpath was being removed under the scheme, and therefore, and obviously the finished road level was more or less the same as existing. So we were dropping at the height of the footpath with 125. So once we reduced it by 125, you could no longer fit a 225 water main across that bridge. And you can see on this photograph here, there are the arch stones, and there's the original water main. They had actually slightly notched the arch stones to get the water main in. Now we were repositioning the water main slightly, and there was no way we were going to cut our way into a national monument. So the compromise was we ended up putting in 2 water mains, a 200 diameter and a 100 diameter water main, fully encased in concrete, because again, we couldn't achieve anything like the normal cover that Irish Water would look for. Some of the other services had to be temporarily diverted and then replaced. and all this work had to be done while maintaining pedestrian and traffic flow across the bridge. So this probably one is, and there's Mick O'Mahony and Eamon O'Mahony for coming over here this evening. One of the big difficulties here was effectively you had a 150-meter long site that at times is 3 meters wide, and you're trying to get materials and machinery over and back on that narrow footprint while you were maintaining pedestrian traffic. You can see on that upper photograph there, their workspace here, the pedestrians are here and the traffic is here. I'll talk about there were 3 different traffic management arrangements. I'll talk about that in a minute. And just some photographs here. The one on the left there shows, so all the valves on the water main were non-standard. So normally this valve would be vertical, but obviously that would have brought it up through the road surface. So it's on its side. This one were off the main span. We were a bit more comfortable once you got off the main spans onto the old spans. But even here, you can see it's at an angle. The 2 valves are at an angle rather than vertical as it would normally be. And all of that had to be recorded, obviously, so that it could be found at a later stage. Right, COVID. The works were stopped twice. The original lockdown from March until May 2020, and then the subsequent lockdown, essentially from the Christmas break in December 20 until early March 21. COVID protocols had to be put in place from March 20 on. March 20 on. And then there were issues around availability of and cost of materials resulting from shortages that became apparent during the COVID. One of those would have been on the decking, and Kieran mentioned the aluminium decking. Ultimately, we changed to a galvanized steel decking because the aluminium just was not available, or not at a reasonable cost. There would have been a very significant uplift in that cost. So very similar system in that it's planks to the aluminium and achieved a very similar result, but just a different material. Just a couple of photographs there. That's for the northern abutment, which is piled in reinforced concrete, and that's one of the arches upside down inside the Max Yard. Okay, where you can see there's your compression connection there with I suppose the fall, and that's your tension connection. Ultimately, that was flipped over then. Traffic management then. Pedestrian traffic across the bridge was maintained at all times, with the one exception of when they were doing the surfacing. For the majority of the work, 2-way vehicular traffic was maintained. While the services were being diverted, vehicular traffic was converted to 1-way southbound, and northbound traffic had to go across the N20 bridge, just to the west. The boardwalk itself, the main structure, was installed over 3 weekends. So there were 6 spans, and 2 spans were installed each weekend. Now we allowed a 4th weekend in case we ran into trouble, but in fact on each weekend the 2 spans got done on the Saturday, and then we had the full weekend, but there was a certain amount of work had to be done to prepare for the next weekend. So there was full closures during that period, apart from there was still pedestrian allowed across the bridge. And then during this resurfacing works, there was full-time night closures for the surfacing works. And again, the surfacing works were complicated because of, I mentioned previously, some of the levels we couldn't touch. So we just, and also bear in mind, we were changing from 2 lanes to 3 lanes. So the center line of the road moved, so the crossfalls all changed. So there was quite a bit of work in terms of establishing. There's a certain amount had to be planed out. Some areas were adding, some areas were taking out, but we were over the 4 spans, the original spans, where there's potential for a water to cross. We couldn't go above the original levels, so that took quite a bit of toing and froing. The photograph here, which you've seen before, that's one-way traffic traveling south. And this is the more normal situation where you two-way traffic. At this stage, the boardwalk was open to the public, so there was works happening in here. Okay, then flooding is the last thing I want to talk about. Okay, obviously we've mentioned in the context of the OPW in the section 50, but the Blackwater, given where it is, Mallow's well down from the source of the Blackwater, it's still surprisingly flashy. The water levels go up and down very quickly, particularly, I'm sorry, I see Ben is here tonight and he'll testify to that. It can rise and fall very quickly, literally in the space of a few hours, that the water levels can go up and down. So the installation of the anchors, the bridge spans, the decking plates all required access from the river, and therefore that had to happen during low flows. The site compound was in the park area beside the bridge, which was flooded on a number of occasions. And to minimize the impact of this, Cumberland literally put their huts up on stilts, and there were protocols in place not to leave stuff lying around over the weekend or whatever, in the event that they literally had a flood and lost stuff. The reason I've included this photograph here is, it's a bit hard to see, but these are the control panels for the traffic lights, but they all look a nice gray. But in fact, the panel is only from there up. From here down is a concrete plinth, and the reason for that concrete plinth is to keep it out of the water in a flood event. So all these are up on all these control panels are up on plinths. This photograph here is during kind of normal flows, and here's some photographs of now these are taken from 2 flood events that happened while the works were in place. You can see the strength of the flow going across the bridge. There's one of the tension points there that you can see the drilling has already taken place. There's Park Road underwater, which is just, the bridge is just off here to you come up Park Road. It's on the north side of, obviously, of the river, and if you come along Park Road, you turn right onto the bridge. Here's some of the cabins on their concrete stilts. And I suppose the reason I put this in is just, I suppose, a sanitary lesson. In a flood event, you get a lot of debris comes down, a lot of kind of small stuff. And if you've any fencing at all, it'll get caught in the fencing, and it'll clog up very quickly and potentially cause a worse flood event to occur. And then finally, this one here, you can see this is the site compound underwater. So this happened twice, I think, during the construction phase, that works had to be suspended, and then the place tidied up afterwards. So I see. Right.